Hello everyone! In my previous video, you saw a 16 times faster version of a complete project AdBlue production, drawn from scratch, from zero to a full working design. In this video, I'll take you behind the scenes and explain step by step how that project was actually created, why I made certain design decisions, and what challenges I faced along the way. You'll see how the layout evolved, from the first idea, through equipment placement, piping connections, and optimization for real industrial use. My goal is to show not just the final drawing, but the real thinking process behind it, the small details, the logic, and sometimes the mistakes that make engineering real. So, let's slow things down, look closer, and explore how a full-scale project is built from a blank screen into a working solution. As you can see, I've already drawn the imaginary building outlines, and now I'm adding the axes. This helps to position the equipment precisely, so all measurements come out as clean round numbers. The video is shown at double speed, just to make the drawing process a bit faster to watch. As I mentioned in the previous video, this 3D model was created based on the PNID scheme, and my own imagination of how to arrange the equipment to work with the. This project will be implemented in a real factory, though some equipment positions will be modified, so the actual location cannot be identified from this YouTube video. The first piece of equipment is the vessel, which is used for heating water, because our AdBlue production unit requires a constant supply of hot water. Let's speed it up for next equipment. Here I'm using a vertical vessel with what's called a skirt, a common type of vessel support. I simply make the skirt straight and turn the nozzle quarter side. As you can see, every task requires quite a bit of mouse work, pushing, rotating, adjusting parameters, and so on. The next piece of equipment we'll add is a pump, a standard horizontal centrifugal pump. Its purpose is to pump the hot water to the reactor, where the urea powder mixes with the heated water. Usually, the pump is placed close to the vessel it draws water from. This helps save space and reduce project costs by keeping the pipelines as short and efficient as possible. Let's speed it up until I place the pump correctly. Nozzle where water comes in from the outside. Let's imagine we're connecting our vessel to the external water supply network. Let's add some valves. First, a check valve to prevent water from flowing backward. I'm adding a simple check valve from the AutoCAD library. Now we're adding a valve from the custom palette, where you can create a valve with any parameters you need. I'm taking the first valve from the list, mainly because I want to place an automatic actuator on top. Later, I can adjust this valve's dimensions at any time. The automatic valve works together with the level transmitter. When the vessel becomes full, the transmitter sends a signal to the automatic valve to close the water line. I've added two ball valves, one with an automatic actuator and the other manual. A check valve, also called a non-return valve, is a mechanical device that allows fluid to flow in only one direction. It automatically prevents backflow, meaning water or any other liquid can move forward through the system but cannot return backward. Inside the valve, there's typically a disc, ball, or flap that opens when fluid flows in the correct direction and closes when the flow reverses. In water systems, check valves protect pumps, tanks, and pipelines from damage caused by reversed flow or pressure surges. Let's connect our pump to the vessel. The suction line comes from the bottom of the vessel to the pump suction inlet. As you can see, it takes many steps to connect the equipment properly. Usually, the pump's connection flanges are smaller than the pipeline size. I've sped it up 4 times to make the process faster. When the line is drawn, we need to add valves. First, we can place a strainer from the pallet. Its longer end should face the direction of flow and be positioned either to the side or downward, because there's a small basket inside that needs to be cleaned from time to time. There are 2 manual valves on both sides of the line. In our case, one is placed at the bottom of the vessel to prevent liquid from flowing to the pump at the wrong time, and the other is near the pump in case we need to service the strainer or the pump. In this setup, it looks a bit unusual because both valves are located quite close to each other. Sometimes the valve is attached directly to the vessel's bottom nozzle, and other times it's placed on the pipeline, especially if the valve is large. For example, butterfly valves are relatively compact, while ball and gate valves tend to be larger. The last element in the suction line is the drainage pipe, a small pipe used to empty the pump line. DN25 usually fits. In this case, our DN100 pipe has a small DN25 branch. To connect these pipes, we usually use what's called a saddle. A saddle, or saddle connection, is a pipe fitting used to create a branch connection on an existing pipeline without cutting or welding a full T. It's shaped like a curved clamp that saddles the main pipe and has a smaller outlet for the branch line. The saddle is attached to the main pipe by welding, bolting, or clamping, depending on the design. Saddles are commonly used for small branches, like DN25 from DN100, in water, air, or chemical systems where you need a quick, simple, and cost-effective way to add a connection point. Let's connect pump discharge line. Let's make a turn close to the discharge nozzle to relieve stress on the nozzles. We shouldn't run the pipe straight from the top of the nozzle, because that can create tension. By bending the pipe this way, we can support it nearby and prevent excessive stress or damage to the pump nozzle. The pump's discharge line goes to the top nozzle of the vessel to allow water recirculation when needed. Another branch will lead to the reactor, where the water will be mixed with urea powder. The standard discharge line valves are usually a check valve and an isolating valve. All valves should be positioned at a height that's comfortable for maintenance personnel to reach. If a valve is located on top of the vessel, a maintenance platform must be installed. Sometimes it's smart to create a few valves that you use often and simply copy them when needed. Of course, there are more advanced methods, like using the AutoCAD spec editor, but for now, I'm showing the simplest way. Draw our line to reactor. I'm not trying to draw the line perfectly from the first mouse click. Sometimes it's easier to draw a simple line first, and then adjust the routing later when you see the full layout. You might even notice smarter connection options that way. This working method suits me well. Now I'm simply copying the vessel and calling it our reactor. Then I'll connect the water pipe to it. This brings us to the end of our first AdBlue production explanation video. I hope it was useful and helped you understand how the system comes together step by step. I'll be happy to answer any questions you have, and if you have comments or suggestions, I'd really like to hear them too. In the next videos, we'll continue building and detailing our plant unit, adding more equipment, automation, and piping connections. Make sure to subscribe and follow along so you don't miss the next stages of this project. Thanks for watching, and see you in the next video.